This example on circuit board layout for electromagnetic compatibility is brought to you by Learn EMC. In this example, we'll look at a printed circuit board layout that does not meet the FCC Class B radiated EMI requirements. We're going to analyze this layout to determine a better design for this board. After taking a look at the original design, we'll make a list of some general EMC goals that we want to address in the new layout. We'll include types of emissions that we want to minimize, as well as issues related to improving immunity. These EMC goals will guide us in determining which aspects of the design might need to be changed in order to improve the EMC performance of the board. We'll implement these changes to give us a new layout that will be much more likely to meet radiated emissions and immunity requirements. Okay, let's get started by taking a close look at the original layout. The clock for this board operates at 125 megahertz. The clock is connected to some digital devices and also to a digital to analog converter. Here's the layer stack up for the board. We've got 6 layers with a ground plane on layer 3 and a power plane on layer 4. The spacing between the layers is 1/4 millimeter. Since the spacing between the power and ground planes is less than 1/2 millimeter, we say that this board has closely spaced power and ground planes. We'll use this fact later when we look at decoupling for the board. The ground layer is a copper plane, however it has a gap as shown by the green shading. This gap extends around the portion of the board with analog signals. The power layer mirrors the ground layer, that is, it also has a gap around the analog portion of the board. This was presumably done to provide an isolated low-noise power and ground for the analog section of the board. Looking at the inputs and outputs for the board, on one side we have a connector that brings DC power onto the board. We also have a digital connector with some unspecified digital inputs and outputs. Notice that we've left off some of the connections on the board, which lets us focus on the issues that are most important. On the other side of the board, we have 2 coaxial cable connectors, one for an analog RF input and the other for an analog RF output. The traces shown in orange carry these 2 signals. These could be NTSC video signals or any other RF analog signal. We'll assume that the frequency of these RF signals could be anywhere from tens of megahertz to hundreds of megahertz. We're going to look closely at this design to try to identify any potential problems. But first, let's take a minute to think about our goals with respect to electromagnetic compatibility for this board. First, we obviously want this board to have low emissions, low enough to easily meet both radiated and conducted emissions requirements. Radiated emissions occur when a source on the board couples to an antenna-like structure. So we want to make sure sources on the board can't couple to antenna structures. Conducted emissions travel off the board on the I/O lines. So we want to minimize coupling to the I/O lines and filter the I/O traces. We also want our board to have good immunity to incoming radiated or conducted noise. The steps we'll take to reduce radiated emissions will also help with radiated immunity. We can reduce conducted noise, such as ESD or electrical fast transients, by making sure that we've adequately diverted incoming transient currents away from potentially susceptible components and circuits. Finally, we want to ensure the integrity of the power distribution on the board, which relates to both emissions and immunity. An important part of addressing power integrity issues is to make sure that the board has adequate decoupling. These EMC goals can apply to any printed circuit board with high-speed circuitry. For this example, we're going to use this list as a guide in determining the changes that need to be made to the board. Okay, let's start with our goal of low radiated emissions. For unintentional radiated emissions to occur, we have to have a source coupled to an antenna-like structure. The source can be any intentional or unintentional signal appearing on the board that has a frequency high enough to radiate. Good candidates for the antenna are structures on or attached to the board that are about 1/10 of a wavelength or larger. To investigate the potential for radiated emissions from this board, we need to identify any structures that can behave as antennas and make sure that none of the sources on the board are capable of driving one of these structures relative to another. The highest frequency identified on this board is the 125 megahertz clock. Assuming that we've controlled the digital transition times adequately, we're unlikely to have sources on the board capable of causing a significant radiated emissions problem above about 1 gigahertz. For frequencies below 1 gigahertz, the most obvious antenna structures are the cables attached to the board and the board itself. We're going to want to identify our ground structure and reference all potential radiating elements to that ground structure. We'll also want to take steps to minimize the amplitude of potential sources and the ability of those sources to couple to antenna structures. The original design for this board has a gap in the ground plane that separates the area under the analog section of the board from the rest of the ground plane. The only connection between these two ground planes is the connection made internal to the DAC. We'll typically see a time-varying voltage on one of these ground planes relative to the other plane. This is not what we want, since this voltage can drive the cables attached to one ground plane relative to the cables attached to the other ground plane. By putting that gap in there, we're essentially enabling a noise voltage that drives the cables attached to the board. As little as 1 millivolt of high-frequency noise between cables attached to a printed circuit board is enough to cause unacceptable radiated emissions. So if the noise voltage across the gap is greater than 1 millivolt at any frequency between 30 megahertz and a gigahertz, we're likely to have unacceptable radiated emissions, and we're not going to meet the FCC Class B spec. In general, we need to keep the voltage between any two connectors below 1 millivolt. However, with that gap in there, it's going to be very difficult for us to control that voltage. So you may wonder why that gap was put in there in the first place. What the designers probably had in mind was that they wanted to prevent the noisy digital currents from returning on the ground plane under the analog devices and coupling to the analog signals. This seems like a reasonable concern, but let's take a minute to think about how high-frequency currents flow on the current return plane. Recall that at RF frequencies, we can control where the return currents flow by just providing a return plane beneath the trace. For example, if we're following the path of this 125 megahertz clock current into the D to A converter, that current is going to return on the ground plane directly underneath that trace, all the way back to the ground pin of the source. On this board, our analog signal is also RF, so the analog return currents are going to behave in the same way. Those currents will come out on the ground pin nearest the trace, and they're going to flow right back to the connector underneath the trace. In well-designed printed circuit boards, the return current for RF signals always flows in a way that minimizes the current loop area. So there's very little likelihood of any significant amount of digital current sharing copper with the analog RF current. This means putting that gap in the ground plane did not do anything to help protect the analog signals, but it did set up a situation that's likely to lead to a radiated emissions problem. If, for some reason, we were concerned about interference at frequencies below 10 kilohertz, we might want to provide an isolated return path for the analog signals. However, low-frequency coupling to RF circuits is usually not a major issue and can generally be addressed by controlling the bandwidth of the receiver. Even if we elected to isolate the return paths of the analog circuits, we would never do this by gapping the ground plane between two external connections on the board. Our first change in the design will be to remove that gap in the ground plane. In the new layout, our ground structure will be a solid plane and will reference all potential radiating elements to that plane. Recall that in this example, the power plane is also gapped. In general, gapping a power plane that's not used as an RF current return path is fine. We might do this if we wanted to provide filtered power to the analog section of the board. In this example, however, there appears to be no reason to gap the power plane, so we'll remove that gap as well. The next issue we want to think about is the location of the external connectors relative to the high-speed circuitry on the board. We've made the argument that a solid ground plane will help prevent potential differences between the cables connected to the board. But this plane serves as a signal current return path, so it is not an equipotential ground. The return currents from high-speed circuitry induce voltage differences between connectors. So when can we expect this to be a problem? A general guideline is that if a return plane between connectors carries tens of milliamps at frequencies of tens of megahertz, it will develop millivolts of potential difference between the connectors. And as we said earlier, a potential difference of as little as 1 millivolt can drive one cable relative to another cable at a level that exceeds radiated emissions requirements. When high-speed circuitry is located between external connectors, the potential difference seen by the connectors will be much larger than it would be otherwise. If we rearrange the board so that the high-speed circuitry is not located between external connectors, the induced voltage will be minimized. Looking at this board, it's pretty clear that there's no way to rearrange the layout so that the high-speed circuitry is not between the connectors unless we move the connectors. With respect to radiated emissions, this original placement of connectors on opposite sides of the board actually represents a very poor design. We want to try to get those connectors closer to each other, ideally on the same side of the board or in the same corner of the board. In the new layout, let's put the connectors along the bottom edge of the board like this. This does not eliminate the voltage between the connectors, since they're still referenced to different points of a current carrying ground plane. But this placement minimizes the voltage differences. If necessary, connectors on the same edge of the board can be referenced to a non-current carrying chassis ground in order to ensure they're held to the same potential. In this case, however, that's not likely to be necessary. So now, in terms of reducing radiated emissions, we've decided on a solid ground plane, and we're going to place the external connectors on one edge of the board. There's one more potential antenna structure that we need to think about. Long traces carrying high-frequency signals can couple energy to other structures. For this reason, we want to try to shorten the length of all traces on the board that carry high-frequency signals. Another good reason to do this is that for short traces, the return current flowing on the ground plane has less opportunity to pick up noise due to common impedance coupling. The 125 MHz clock current is certainly a high-frequency signal. Notice that the clock traces, shown in blue, are longer than necessary. In the new design, we'll move the clock and other components to keep the clock traces short. We also want to shorten traces carrying the digital signals where possible. The analog RF signal traces, shown in orange, also carry high-frequency signals, and we'll shorten those in the new layout by moving the DAC closer to the analog RF connectors. So in our new layout, we're going to try to shorten all the high-speed traces on the board. One additional note. We'll want to ensure that the transition time of the clock signal is controlled. A 125 MHz clock should generally have a transition time of at least 1 nanosecond. Here, a single clock driver drives 3 clock inputs, so the transition time is probably self-limited by the internal resistance of the driver. In situations where the specifications of the clock driver do not inherently limit the transition time, we'll generally want to add a series resistance to make sure the transition times are not faster than needed. Now let's talk about conducted emissions. Conducted emissions travel off the board on the I/O lines. We can minimize conducted emissions by minimizing coupling to the I/O lines and by filtering the I/O traces. We can reduce coupling to the analog I/O lines by shortening the traces and by preventing digital return currents from flowing on the ground plane under the traces. We discussed both of these steps earlier in terms of radiated emissions, so we don't need to make any additional changes to reduce coupling to the analog I/O lines. Concerning filtering the I/O traces, we should generally provide filtering on every trace that carries a signal onto or off the board unless we can demonstrate that it's not required. We also want to filter the power input, which may be connected to an unshielded cable. So let's add filter I/O traces to our list of design changes. In this example, we'll implement these filters by connecting a capacitor from the I/O trace to the ground plane with a low inductance connection. The next issue we want to address is immunity, beginning with radiated immunity. We want our circuit board to have immunity to radiated signals from sources off the board. Fortunately, the steps we took to reduce radiated emissions should, in this case, also ensure adequate radiated immunity. This works because the same antenna structures and coupling mechanisms are involved in both radiated emissions and radiated interference. We also want robust immunity to electrostatic discharge and electrical fast transients. Both of these types of noise can enter the circuit board on the I/O lines. The best way to reduce the impact of these types of conducted interference is to filter or add transient protection to the I/O lines. Recall that we decided to filter the I/O lines and the power input when we discussed low conducted emissions. The same filtering will give us some immunity to ESD and electrical fast transients. However, I/O traces that connect sensitive components to the external environment may need varistors or some other form of transient protection as well. Our final goal for this circuit board is power integrity, which relates to both immunity and emissions. We want our power bus to deliver a consistent voltage to the devices on the board so that they operate properly. We also want to make sure that noise on the power bus doesn't lead to unacceptable emissions. Adequate decoupling is important for addressing both of these potential problems. We need to determine whether the existing decoupling is adequate for this circuit board. Since this board has closely spaced power and ground planes, all of the decoupling is global. This means we can scatter decoupling capacitors around the board without worrying about placing them very close to active devices. However, we do need to make sure that we have enough decoupling capacitors and that each capacitor is well connected to the planes. In general, we want a minimum of 1 decoupling capacitor for every power pin of every active device. On this board, it looks like we have 5 active devices, and a couple of them have multiple power pins. So the 3 decoupling capacitors we have are probably not adequate. We haven't specified the dimensions of this board, but it's likely that there is some overlap between the power bus resonant frequencies and harmonics of the digital signals. Additional well-connected decoupling capacitors will help dampen these resonances. Decoupling capacitors are inexpensive and they don't take up much space, so in the new layout, we'll add several more. We also need to make sure that each of our decoupling capacitors is well connected to the power and ground planes. The 3 decoupling capacitors shown here are connected to the planes through traces. This is never the right way to connect a decoupling capacitor to a board with power and ground planes. For effective decoupling, we need to minimize the current loop area for each capacitor connection. We can do this by eliminating the traces and locating the vias close together. This is the way we're going to connect all of the decoupling capacitors in the new layout. We'll use this symbol on the diagram to represent a decoupling capacitor connected to the planes with vias adjacent to the pads. Finally, depending on the specific devices used and the quality of the power input, additional bulk decoupling may be needed. We'll go ahead and add bulk decoupling near the power supply in the new layout. Now we're ready to take a look at a new layout that incorporates all of these changes. Here's the original design on the left and the new layout on the right. Notice that some of the components have been rotated relative to their original orientation. We did this to help keep traces short. We improved the power integrity of the board by adding additional well-connected global decoupling capacitors. We moved the external connectors to one side of the board. The original design isolated the coaxial cables on one side of the board from the digital and power cables on the other side of the board. All of the high-frequency sources were between these cables. It's extremely unlikely that a design like this would meet radiated emissions requirements. The new design locates all cable connections on one side of the board where they can be more easily referenced to the same ground potential. It also better contains the RF power through the use of effective filtering and better routing of traces. The new design is more immune to radiated interference for the same reasons. Note that RF energy picked up by the cables in the original design causes RF current to be routed through the DAC, which was the only connection between the two sides of the unintentional antenna created by that gap in the ground plane. Low-frequency conducted emissions have been dealt with primarily through filtering, and high-frequency conducted emissions through both filtering and a layout that reduces coupling to the I/O traces. We've improved immunity to electrostatic discharge and other electrical transients by referencing all cables to the same low-impedance ground and by providing shunt capacitors or transient protection on the I/O traces. In the original layout, any transient current coming in on a coaxial cable shield that was trying to get to building ground was forced to flow through the DAC ground. In the new layout, any current coming in on one cable and going out on another has a relatively low impedance path. Note that low-frequency currents coming in on one cable shield and flowing out on another are not prevented from flowing onto the board's ground plane. In many applications, this is fine. However, in some industrial, automotive, or aerospace applications, it may be necessary to isolate the chassis ground from the board's ground plane at low frequencies. This new layout is significantly more likely to meet radiated and conducted emissions requirements. Visit the Learn EMC website for additional examples and detailed tutorials on EMC topics, including printed circuit board layout, circuit board decoupling, and identifying current paths.